Hi everyone and welcome to today's video. So we're going to be looking at the third type of differential equations. So we're going to be dealing with linear differential equations. What are they and how do we work with linear differential equations? Find out in today's video. Alright, so next we'll look at the third kind of differential equation. So these are actually linear differential equations. So now what if you've come through a case where the differential equation is not separable, it's not homogeneous? So what is that? Now the situation is it may actually now be a linear differential equation. So you remember that when you want to see if a differential equation is actually separable, is you try to group different variables together that actually look the same. If that is possible, it is actually separable. And then remember that actually when we want to prove that actually a differential equation is homogeneous, we actually try to compare the dimensions on both sides. And if they're actually equal, we say that that is homogeneous. But now what if there is a case where even after testing the dimensions, they are actually not again equal? So that situation is, it may actually be a linear differential equation. So if a non-separable differential equation is not homogeneous, it is a linear differential equation. So it is in the form dy dx plus py is equal to q, where p and q are functions of x. So for example, consider the differential equation dy dx plus 2xy is equal to x. In this case, the dimensions are, as you can see, we have L over L plus, this should actually be L times L is equal to L. As you can already see, we'll have 1 plus L squared is equal to L. So hence, this is not homogeneous. So since the dimensions are not the same, then it's not homogeneous. Also, since its variables cannot be separated, it is not separable. Hence, the equation is linear. So solving linear differential equations, how do we solve them? So such equations can be solved with the help of the integrating factor. So consider the general form of linear differential equations below. So this is usually the general form of how linear differential equations look. So note that the coefficient of dy dx is equal to 1. So that is very, very important. The coefficient here must actually always be equal to 1. So calculate the integrating factor r using the formula r is equal to e and then to the power integral of p dx. So whatever value of p here is going to be in the integral, and then that's what how we're going to find the integrating factor. So multiply the integrating factor throughout the differential equation, then we'll have r dy dx plus r p y is equal to q r. Then lastly, we can see that the left hand side is a derivative of dy dx y times r. So therefore that means we'll end up having d dx times yr is equal to qr. So these are the simple steps that we take to actually solve a linear differential equation. But I believe that this will actually make more sense as we actually work on it practically. So in the last step, we simply integrate both sides with respect to x and get the constant c to find the solution. So that's what we're going to be doing. So let's look at the first example. So this is a question from UNEB 2019 and this was question 16b. So I'm being told to solve the differential equation dy dx plus y cot x is equal to x, given that y is equal to 1 when x is equal to pi over 2. As I've already said, first test and see if it is separable or whether it's homogeneous. So once you realize it's not separable and it's not homogeneous, you can actually see that it is actually now a linear differential equation, because I can already see that this is L over L plus L times L, which is actually L squared is equal to L. So this is definitely not homogeneous, as I can already see. And then what I can now see is this is actually now a linear differential equation. So this is what I have right there. So it's actually in the form dy dx plus py is equal to q. So where this is y, and then cot x shall actually be representing p, and then x shall actually be representing q, as I can already see. So now we're going to first find the integrating factor. So remember the integrating factor r is equal to e to the power integral of p dx. So what is our value of p? So this is y. So that means that the value of p must actually be equal to cot x. So we're going to place cot x there. So what is the integral of cot x? So the integral of cot x should actually be equal to ln sine x. So we now have r equal to e to the power ln sine x, of which we know that an e cancels out a ln. So we'll be left with r is equal to sine x. Now multiplying the integrating factor throughout the differential equation, that's the next step. So we'll have it here. So sine x shall be multiplied throughout. So we'll have sine x dy dx plus y sine x cot x is equal to x sine x. So now we can see that. Now the next step is now to actually realize that the left hand side here is actually a derivative of this. And how do we find this? So we can see that this is actually a derivative of d dx into bracket y sine x. And how did we do that? We remember that from our formulas that now all you have to do is, it's actually just a derivative of y times r, which is the same as y times sine x, because r is actually sine x. Remember, it is d dx into bracket y r, but r is sine x. So it's as simple as that. So now we'll have d dx y sine x is equal to x sine x, which is the value on the right hand side. Alright, so the next step is to integrate both sides. So we're going to integrate it this way. Now, something that you need to know that is a new concept in this part is an integral always cancels out a derivative. So once you combine an integral with a derivative, they all cancel out and you'll be left with y sine x on the left hand side being equal to the integral of x sine x dx. So all you have to now focus on is the value on the right hand side. Now for the right hand side, which is the integral of x sine x dx, we actually solve that using integration by parts. So we're going to let u be equal to x, and then dv dx should actually be equal to sine x. So you can already say that du should actually be equal to du dx should actually be equal to 1, and then to find v, we're actually going to integrate sine x. So v should actually be equal to negative cos x. So remember that when you're integrating by parts, this is going to be the formula. So when you plug in all the values that we found, we'll have this. So we'll be having negative x cos x minus the integral of negative cos x times 1 dx. Now this negative cancels out with that and we'll have a positive. So this is what we end up with. So now next we have to find the integral of cos x, which is definitely sine x. So we have negative x cos x plus sine x plus c for the value on the right hand side. So we now have y sine x. So now we take this answer here back here, then we will now have y sine x is equal to negative x cos x plus sine x plus c. Now that we have that, we can actually now consider what conditions have actually been given. So in the question we're being told, given that y is equal to 1 when x is equal to pi over 2. So we're going to substitute y is equal to 1 when x is equal to pi over 2. So where there is y, we're going to actually place 1. So we now have y times sine pi over 2 is equal to negative pi over 2 cos pi over 2 plus sine pi over 2 plus c. Now what you should add, pi over 2 is basically 90 degrees. Now from here, cos of 90 is 0. So all this cancels out. And then from here, we can see that sine of 90 is actually 1. And then here we shall also have 1. So 1 times 1 is 1. And then here we shall only have 1 because this actually cancels out. So I can say that I have 1 is equal to 0 plus 1 plus c. So 1 is equal to 1 plus c, of which c should actually now be equal to 0. So now that means that when we substitute for c in equation 1, we shall have y is equal to y sine x is equal to negative x cos x plus sine x plus 0, of which it's just basically y sine x is equal to negative cos x plus sine x. And then if I rearrange this, let's rearrange this, I'll have it as sine x minus x cos x. This is our answer. Alright, so we move to the next question. The next one is from UNEB 2010, and this was question number 8. So we're given to solve the differential equation x dy dx plus y is equal to e(x). So when someone looks at this number, they may be like, okay, this is, if I look at the dimension, this is L, this is L over L plus L is equal to L. And then you can actually see that this is going to end up as this L over L will cancel and we'll have L plus L is equal to L. Now someone may think that that actually means that this is homogeneous, but not necessarily in this case. Now in this case, this is actually still linear. What happens is, another of knowing if a function or a differential equation is linear is we look at if it can be arranged in the form dy dx plus py is equal to q. So this one can actually be arranged in that form, and actually I want to show you how. Remember that when we're dealing with linear differential equations, we want to make sure there is no coefficient in front of dy dx. So is it possible in this case? So let's say that So actually, if we divide everything all through by x, we can end up with dy dx plus y over x is equal to e x over x. So now having it in this format actually puts it in that form. So what you can already see is we already have the y value here, and then 1 over x will actually represent p, and then equals to, then hold this entire value will actually represent q. So this is actually a linear differential equation. So next we're going to find the integrating factor. So you can already say that r shall now be equal to e to the integral of p. Now the p value here is actually clearly 1 over x. So that's what we get as the integral. So it's now the integral of 1 over x, which is ln. But remember that when we have an e of the ln, the e cancels out the ln, and then we shall remain with r is equal to x. Alright, so next, multiplying the integrating factor throughout the differential equation, we'll have it as x dy dx plus x times y over x is equal to x into bracket ex over x. Now in this case, as we've already said, this left hand side is the derivative of y times x. And why is that? It's like we said in all the steps at the very beginning. It's going to be y times the derivative that you actually have here. So this entire side is actually the derivative of y times r. It's a derivative of yr, of which in our case r is x. That's why we have it as yx, being equal to this value on the right hand side, which is what we have right now. So now you can already say this x and this x will cancel and be left with ex. So be left with the derivative of yx being equal to ex. I mean d dx yx is going to be equal to ex. Now we're going to integrate both sides by introducing the integral. Now something very important also is an integral also cancels out a derivative every time we introduce it. So this integral will cancel out the d dx and we'll be left with the yx. So we'll be left with yx being equal to the integral to get from this right hand side, which the integral of ex shall actually be ex plus c, and this is the answer that we're looking for. Alright, so let's move on to the next question. So next question is a question from UNEB 2004, and this was question 16a. So being told to solve the differential equation tan x dy dx minus y is equal to sine squared x. So when I look at this also, I can already see that this can actually also be arranged as a linear differential equation. So I don't even need to test anything, but it's actually clearly a linear differential equation. But if I were to, this would actually have been L times L over L minus L. Of course, this and this will cancel. So I'll be left with L minus L on the left hand side being equal to sine squared, which is L squared. So that will actually show that this is actually also linear and not homogeneous. But even apart from that, I can already say that it can actually be arranged in the form dy dx plus py is equal to q. Let's see what I mean. So remember, we don't want a coefficient in front of dy dx, so we're going to divide all through by tan x. So we'll have dy dx minus y over tan x is equal to sine squared x over tan x. Now when we have it this way, remember that the form of linear differential equations, it should be dy dx plus y being equal to q. I mean plus py is equal to q. Now what that means when we have a minus sign here is it simply means that the value of p actually has a negative. So that's the difference. So we can actually put it in this form dy dx plus into bracket negative y over tan x is equal to sine squared x over tan x. So that just simply means that we have a negative p, of which the p value is actually going to be equal to negative 1 over tan x. So finding the integrating factor of p, so p should actually be equal to negative 1 over tan x. Now a 1 over tan x is the same as cot x, so we have a negative cot x. Now the integral of cot x is going to be ln sine x, but now we'll have a negative ln sine x. So remember, from properties from natural logarithms, you can actually take this negative here and actually make it the power. So we'll have sine x to the power negative 1, which is the same as 1 over sine x. Now from also the rules of exponentials, you know that an e cancels out a ln, so we'll be left with r being equal to 1 over sine x. Alright, so multiplying the integrating factor throughout the differential equation, we will have 1 over sine x dy dx plus 1 over sine x into bracket negative y over tan x equal to 1 over sine x times sine squared x over tan x. So now we can now see that the value on the left hand side, this entire value is actually the derivative of y times 1, I mean it's the derivative of yr, which is y times 1 over sine x, being equal to this value here on the left hand side. Now this is what we'll end up having. So this is y over sine x being equal to 1 over sine x sine squared x over tan x. Now you can already see that this and this reduce and we'll be left with sine x over tan x. So now this value on the right hand side is the same as sine x divided by tan x, but remember tan x represents sine x over cos x. Now when we change this value to a multiplication sign, we'll have cos x over sine x, of which this and this cancel, and we'll be left with d dx y over sine x is equal to cos x. So integrating both sides, we'll have the integral of that. Now remember that the integral sign will actually cancel the d dx, so we'll be left with y over sine x being equal to, now the integral of sine of cos x is going to be equal to sine x plus c, and this is our answer. Alright, so question number 4 is the question from UNEB 2008, and this was question number 16a. So having to solve the differential equation x dy dx minus y is equal to x cubed e x squared. So if you test everything, so this one you just need to test the dimensions. When I test the dimensions, I can already see that this is actually a linear differential equation, but also I can also see that it can also be arranged into the format dy dx plus py is equal to q. Alright, so let's solve this, but now we can clearly see we need to eliminate the coefficient from dy dx, so we have to divide all through by x. So when you do that, we'll have dy dx minus y over x is equal to x cubed ex squared over x. But now from our rules of linear differential equations, this must actually be a plus. So that this simply means is p is actually a negative 1 over x. So this can actually be arranged this way. So have dy dx plus into bracket negative y over x being equal to x cubed ex squared over x. So that simply means that our value of p is negative 1 over x. So finding the integrating factor, which is r e to the power of integral p dx, we'll have the integral of negative 1 over x, which should actually be negative ln x. So taking a negative sign and making it the power, we'll have it that way, which is actually 1 over x. So we have it as ln 1 over x. Now remember that an e cancels out a ln, so we'll be left with r being equal to 1 over x. So multiplying the integrating factor throughout the differential equation, we'll have y 1 over x dy dx plus 1 over x times negative y over x being equal to 1 over x into bracket x cubed ex squared over x. So this is what we actually have when we actually simplify that even further. So when I multiply this in, this is what I have, x cubed ex squared over x squared. So I can see that this and this reduce, and I'll be left with x ex squared. Now I can clearly see that the value on the left hand side, which is this entire value, is the integral of, it's the derivative of d dxy r. So this is y times r, of which r was 1 over x being equal to the value on the right hand side. So I will have y over x being equal to x ex squared, as you can see right there. So next I can integrate both sides, and this is what I'll have. But remember, this integral sign cancels out this derivative, and I'll be left with y over x being equal to this integral right there. So I end up with y over x being equal to the integral of x e to the power x squared dx. Now the value on the right hand side can be solved using U-substitution. So we're going to first deal with that value on the right hand side. So I'm going to let u to be equal to x squared, which du dx should actually be equal to 2x, and then dx, if made the subject, should actually be equal to du over 2x. So that means therefore we have the integral of x e to the power u times du over 2x. So you can see that this x and this x cancel, and we'll be left with eu in the integral. So we'll be left with a half to the integral of eu du, which the answer is a half eu plus c. But u is x squared, so we'll have the integral of x times e to the power x squared dx should actually be equal to a half e x squared plus c. So therefore we now have, so if we take that back, we'll have y over x being equal to a half e to the power x squared plus c, and that is our answer. Alright, so the next question is a question from UNEB 1990, and it was question 3a. So being told to solve the differential equation dy dx plus y cot x is equal to 3 sine x cos x. So without testing anything, I can already say that this is already arranged in the form dy dx plus py is equal to q. So this is already clearly a linear differential equation. So now I can already see that the p value is already clearly cot x. So this is py, so p is clearly cot x. So finding the integrating factor, which is e to the power of the integral of p dx, we know the p value is cot x, so now dealing with the integral of cot x. So we now have, it's going to be actually ln sine x, so we now have r to the power e ln sine x, of which we know that the e cancels the ln and we'll be left with r being cot sine x. So multiplying the integrating factor throughout the differential equation, we'll have sine x dy dx plus y sine x cot x being equal to 3 sine squared x cos x. So that's what we actually have right now. Now we can now see that the value on the left hand side is clearly the derivative of y sine x, or yr, of which r was sine x, being equal to this value on the right hand side. So now we're going to integrate both sides. So introducing the integral, this is what we'll have. But remember, the integral sign will actually cancel the d dx and we'll be left with y sine x being equal to the integral of the value on the right hand side. So this is what we're left with right now. Now if we were to deal with the value on the right hand side, that can actually be solved using U-substitution. So we are going to let u to actually be equal to sine x, du dx should actually be equal to cos x, and then dx should actually be equal to du over cos x. So therefore this is what we end up having. So you can actually say that this cos x and this cos x cancel and to be left with the integral of 3 into the integral of u squared du. Now remember that if we integrate u squared, we'll have u cubed over 3. Now you can say that this 3 and this 3 cancel and then we'll be left with u cubed plus c. But remember that u is actually sine x, so we have sine cubed x plus c. So we're going to take that back and therefore we now have y sine x being equal to sine cubed x plus c, and that is our answer. Alright, so I have an exercise for you. I encourage you to try these numbers out. So the answers are actually right on the right hand side in the brown color. So you can actually test that out and then compare your final answers to what I have right there. And I believe that after you've done that, you'd have perfected your knowledge of linear differential equations. Thank you so much for watching.
Thank you so much for watching this video. I hope the video really helped you. I hope the numbers were sufficient for you. If this video was of help to you, feel free to give the video a like, a thumbs up, and then feel free to share the video with all those that you can and help them out if the video really helped you. And then you can leave a comment down in the comment section for me and I'll get time to reply to you. Thank you so much for watching. I'll see you in the next video.